Hi, I'm Eric Beatty, and this is the presentation for my 691 capstone project, Reinforcement Learning with a Robot. This presentation is going to primarily cover two Jupyter notebooks along with PowerPoint slides that cover some of the algorithm details as well as some of the robot and some of the test cell. To get started, what is Q reinforcement learning? Q reinforcement learning is a model-free machine learning algorithm. It has an agent that moves through an environment. There's a Q table that contains all the possible states that the robot can exist in as it moves through the environment. A set of states are the locations of the Q table. An action is what moves the agent from state to state through the environment through the Q table. A reward is given to the agent for taking any action, and then this reward is used to calculate a Q value along with past rewards based on the current reward plus some past rewards based on the state. This slide here gives a graphical representation of the steps taken during the reinforcement learning algorithm. You have your agent that takes an action. That action gets fed into the agent into the environment. The result is a reward and then change of state. Next, that Q table is updated for the previous state you were just in. Down here is a representation of a Q table based on states and actions. And the Q table is filled out for each action in a given state. The Q table is filled with Q values. And Q values are generated through experience. Each action taken will create a reward, and then that reward can be used in conjunction with previous rewards so that you can have a algorithm that learns through experience. And then that amount of learning is impacted by two training parameters. The alpha learning rate, which is kind of like a scalar of the difference between what is the best known reward for an action minus what the current reward is. So notice that it is max Q of st plus 1, which means it's looking into the future, assuming you're going to be taking the action that'll put you in the future state, assuming that's the reward you're going to be getting. And then the gamma discount factor is used to adjust the gain, the amount of impact that maximum reward will have for the future state. And then in reality, what you really are doing is you are in a state and then you're transitioning to a new state. So you're not really looking into the future, you're using your past experience to tell you what action to take to move into a state, and then after you've moved in that state and generated a reward, you go back and update the Q table for your last state. Moving on to the robot. The robot is just a collection of servos that have these brackets put together so that it has the ability to move in a way that looks like a robot. So it's a bunch of motors pieced together so that it looks like it has arms, looks like it has legs, and then there are degrees of freedom that mimic human motions. And these robots are controlled, these servos are controlled through a pulse that is PWM'd. And in this project, some of those servos, specifically the ones that would make up the leg, that would allow the leg to move, like you can imagine you are kicking your leg straight out and bending your knee. So in that motion, not for for this part, not side to side. So for these three servos, so you can think of it as a hip, knee, and ankle. These three were, there was some transforms done on them that made it possible to, instead of using a bunch of PWM values to set the orientation, the rotational angle, they were transformed so that you could input an XY value to put what would be a point on the foot into an XY Cartesian coordinate. So you can imagine you are looking at a side view, and this here would be like a fixed length for the upper part of the leg, and this would be a fixed length for the lower part of the leg. So below the knee, this would be the knee, this would be your ankle, and then this would be your foot. And you can piece together the equations you would need to convert this backwards into making these angles. So you can solve for theta hip, and then theta f for foot or ankle, and then c would be the angle of the knee. And then once you have the ability to define a set of xy coordinates, you can come up with a grid, and then you can implement that grid into a Q table. And for this project, there were two different implementations of the environment. The first one, the thinking was there will be a big Q table with a lot of possibilities for the foot to fill, and through a lot of small motions, the algorithm will learn to move in kind of a circular pattern that you can imagine if you were to plot your foot from a side view onto an XY Cartesian coordinate. You think about motion, your foot as it moves, lifts, goes forward, hits the ground, and so on and so forth. It would make a circular motion. Thinking would be with the right combination of sensors and the Q-learning algorithm that the robot could learn to recreate those motions and actually walk. And then that did not work. I'll go into details later. The second implementation reduced the number of XY coordinates down to a fixed X. So that X meaning the distance in front of and behind the robot, and then two different Y values. So that would be like how much bend the knee has. And those were they were picked arbitrarily just to see, just because one, well, not totally arbitrarily. They were picked because I was able to actually get the robot to walk with one XY pair, and then I added another one on top of that, just so the learning algorithm could have some room to figure out if there's something better there. And then in future implementations, it could be grown even more. This project has really laid the foundation for something that the robot is able to walk, but there's definitely room for improvement. And this algorithm would be the way to do it, given enough time. All right, moving on. This is the test cell. The robot was able to move along this linear path on this wooden track. There's a divider in the middle to keep the robot oriented in the right direction, because sometimes it would start to veer off to the left and right. There are two servos fixed up here. They're on the top. There's one fixed back here. This one appears on a linear rail that allows the robot to move. Once the robot reaches a certain distance to the left here, or if it falls over, this servo would pick the robot up, and then there's a servo right here that bring it back, and the servo would let it down back into a fixed starting position. And here you can see the sensors that make up the data collected for the environment. There is 2 distance sensors here that detect the change and distance for each foot. And then there's an accelerometer here, a 3-axis accelerometer mounted to the head that can detect leaning. The robot was controlled through, programmed through LabVIEW, and then there were 3 different devices that were used. There's a PC that interfaced with the Jupyter Notebook. There's a MyRio that handled the communication between the PC and the FPGA, and there was an FPGA that actually does the hardware control. So it sets out all the digital signals, reads in all the other signals. Okay, with that background out of the way, now we'll jump over to one of the 2 Jupyter Notebooks I want to cover. So there were 2 different environments I used. So this one is the second one. The first one's pretty much the same. I don't want to cover it because it's covering a lot of things. The main difference was the environment was different, and then some of the training steps were a little bit different. I'll discuss what those were, but the learning algorithm was the same. So the first step is to do our normal imports. And then down here, there's a directory. The working directory has changed so that we can save some of the learning data to a network drive. And this step builds the Q table. So there were 5 rows, which means there are 5 different Y values that the robot's allowed to learn through. I had the X values fixed, and you'll see how that works, but so there was 5 values for training for the X, Y coordinates, so 5 different Ys. And then one thing that the second iteration of this program did was it implemented the ability for the robot to lean left and right. And it does that by actuating the servos for the hips that would bend like at the waist to the left and right, and then also for the ankles to lean left and right. So there are hip roll equals 5 means there's 5 different angles that the robot could take, and then hip roll opposite means let me take a step back. This implemented a system of allowing the robot to lean left and right, and the LabVIEW portion controlled that by alternating which leg the weight of the robot is going to be on. So you went left, right, left, right, left, right. Hip roll equals 5. Hip roll here is there are 5 angles for the leg that has the weight resting on it. And then hip roll opposite means there are 5 angles for the other leg. So each step the angle would offset, and that's why you see there's a leg left right part of this table as well. And then ankle roll means it's the same thing. So if on your left leg, you're going to have a set of these values, which is going to apply to, so this will apply to the left leg, this will mean lean to the left, and this will apply to the right leg. And then when the leg is right, this will mean lean right, this will mean lean right, this will apply to the left leg. And number of steps is a way of training the robot to chain multiple actions together. So one step can impact the other. And then the number of actions is the 16 means there are 16 unique ways the robot can move through these different dimensions. Some of these were fixed, like no matter what, each step, this would change left, right, left, right, left, right. So there's no control through that. Number of steps would also always increase. So the actions here were actually defined by, these 16 actions are defined by these four dimensions. And here, these lists are used to record the appropriate or the corresponding name here. So this one builds a list of the actions taken. This one builds a list of the rewards given, and this one builds a list of the episode number, so that those can be saved and then retrieved later to look at the results. This is not necessarily implemented in the results here, but this was an experiment done that is an important step in future iterations of this project, and that would be that the data we collect here, this shows that I can load those Q values into another table that's bigger. So I can take what's been learned here and then use it when I want to expand the scope of the environment, and I don't have to start from scratch again necessarily. So there could be some value in having previously learned, even if it's in a different environment, a slightly smaller environment. This function here is used for sending messages over TCP to the PC. The PC has a TCP server that runs in LabVIEW that just sits there and waits to receive a message, and then depending on what the message is, it'll contain the instructions to something like move to the servos to a new position, or to move the robot back into the starting position. Get message and get environment data. So get message just gets a string from the PC, and then get environment data uses get message to get all the environmental data as well as some of the other test parameters that LabVIEW has. So it gets the accelerometer data. It gets middle distance, which was a distance sensor that was used in the first version that was actually removed. So at one point in time there were 3 sensors, but it ended up getting reduced down to 2 when one of them was found to be useless. It was a sensor mounted to the body of the robot facing outward, but a lot of times the robot wouldn't necessarily move, even though a foot or leg moved in a positive way that needed to be recorded. So it was either no data or just redundant data, so it was taken out. But since it had already been scripted here, it was easier to leave it in and then just add things onto the end, since it didn't really seem to impact negatively the script. In-stop is used to indicate the robot has reached the end of the training track and that testing needs to stop. Lift is used to for the PC to tell the Python script that the lift sequence is still running, and to wait. Move is the same thing, except for it's used for LabVIEW, the PC, to tell the Python script that a move instruction is still being executed. Right distance is the distance gained or lost during any step by the right foot or the left foot. Extend means there's an extend subroutine, just like left and move. And this is used to tell the Python script if the extend routine is still running. And then debug is a Boolean set by the PC to enable some stops, some pauses in the main script that does the learning, so you can slow things down and you can look at the data and make sure everything's working correctly. Terminal state is used to signal that you have reached the end of a training episode for either the robot has fallen over or it has reached a specific number of steps or an end stop or distance. And then some of these actually were used in the first version and then taken out for this one. So version 2 actually only looks at the accelerometer and the end stop. Get next action. So get next action is a function that looks at the Q table and takes in a training parameter called epsilon. And what this will do is it will take whatever state you're in, and since the current state is influenced, the current state is Q value is influenced by the reward generated from transitioning from that state to the next state. You can know that like when you are in any one state, you have the action that should result in the maximum reward. So this NP argmax will tell you the location in the Q table. So there's we're looking at the actions dimension of the Q table, and in the actions dimension of the Q table there's a bunch of Q values, and whichever has the maximum Q value, whatever position that is the action to take. Or you can take a random action, which is really useful for when you are trying to not get stuck in a local minima, or you're just trying to find alternative, possibly better actions to take than you've already learned. Get outputs. This will transform it transforms the state numbers. So you're in some state, it's just defined by number. This takes that number and converts it to the parameters that the PC needs to actually move the servos. Get next location. So this is after you've gotten an action and you have all the state variables. This looks to see if the action you have is first is if it's possible to do, and if it is possible, it updates the state variables to the new variables. So, for example, an action of 0 would mean you're moving to the left in all the environmental variables for those 4 that we mentioned before. And then it goes down, so you have some that move left, then some that move right, and then some that move all right. So you can imagine that you're moving through a whole bunch of two-dimensionally, but it ends up being, you're working in 4 dimensions. Now, here we have the bulk of the actual Q-learning algorithm. Starts with defining the epsilon. So epsilon was used to get the next action. So here, with the epsilon is 0, if I go back up to the get next action, if it's 0, this will always evaluate true or false. So we'll always do a random action. And then the higher you make this, the less likely you are to take a random action and to always do what the best learned action is from the Q table. Discount factor and learning rate, those are used in the Bellman equation. Steps is the number of steps that the robot has taken in any episode. And then here, this for loop defines the loop that actually runs the training algorithm. And here it's set to run for 300 episodes. An episode is defined as An episode is a loop, an iteration through this for loop that ends whenever you reach a terminal state. So one full episode would be the robot making it to the end and setting the endpoint variable true. Episode sets tracks the number of steps taken in any one episode, which is a good learning metric. So as the robot becomes more successful, you should see a decrease in the number of steps taken, since the algorithm looks to maximize profit. In this case, we'll get down to the reward. This will make more sense, but the reward is mostly made up of distance gained per step. And this step lifts the robot, so no matter where it is, it lifts it and it puts it back down into its starting state. Here it's waiting for that lift subroutine to finish, and then extend it extends the retraction line. So there's a cord that pulls the robot back, and then you have to unwind that cord so the robot can walk forward again. And this here just defines a starting position for the robot to be, so it's its starting stance. So this is X's of 0 mean the feet are directly underneath the robot, and then 171 means the knees are crouched, or it's starting from a crouching position. And just so you understand what these numbers mean, without going into too much detail, I measured the length of the robot, and then I defined the conversions to be from PWM to millimeters of the robot. So if I were to put in 0 and then the total length of the leg, which is 179 millimeters, that would be standing straight up. On leg 0 means we're going to start out being on its left leg, which will mean it being on that leg means it's the leg that actually will be doing the moving. So if when I say moving, this algorithm has the robot lean one way or the other, and the side it's leaning to, it considers that foot to be stationary on the ground, and the other leg moves relative to where that foot is. So it's send message, then sends move, which the PC sees, and then it sends these XY coordinates to the transform, which converts them to the PWM, which then goes to the rest of the hardware, and the servos move. If debug is true, and then this will pause the script right here until you hit enter on the keyboard. And then here, we're in a while loop that is actually the episode. When you exit this while loop, that means you are out. The episode is over. It goes back to the top of the for loop, and it starts over again. So it waits until the terminal state is true. All right, action index is getting the next action based on the current state plus epsilon. Here we just print out for visual sake of what the number step is. So num step is the number goes from 0 to 3, so there's 4 different steps you link together, and then action, and there's a number of 0 through 15. And then we record what the old Q values are. So we have our action, and now we have our action, we can actually update what our new state should be. But before we do that, we record what the old state is, so we can use it to enter in the Bellman equation at the end. Here we update the step, and then say since there's 4 steps, if this equals 4, we put it back to 0, and then if we switch which leg we're leaning on. And then here is where the x part of the xy coordinate is fixed. So it's either going to be 20 or negative 20. And then in future iterations of this would be expanded along with possibly more y values. And here we get the next location based on the action we received from get next action. And then we write to our list for storing for later. And then send message 0. This zeroes out the distance sensor, so we haven't taken a step yet. We want to measure the distance gained in a step, so we zero out what the reading is on the distance sensor. Then we take an action and we record that we're recording the difference between where we were and where we are at the end of that. And then these in here are kind of like a buffer because there's actually some communication going on, so it's not necessarily going to be instantaneous, so this kind of allows for the message to get sent. And then we print out here just so we can see what's going on. What this is for is let's say you're on your left leg and you are in a specific row, and then we're saying now we're leaning on our right leg, but we want our left leg to remain in the same row as it ended. So here, that's what this is used for. Here we're getting outputs, so we're getting the XY coordinates, and then those XY coordinates are being sent. And then notice if the leg is left or right, it depends on, that affects where the row out variable goes. So we get a new row out if, for whichever leg we are now have transitioned to. And then we get environmental data, which then we can use to see if the move is still happening. And then once it's finished, we wait just a bit for the robot to stop moving, because sometimes it's a rigid structure and there's some shaking. Then we get the distance. We use this here to get the final distance, which gets printed here. And then part of the reward algorithm, or the reward, it is made up of 3 things. So the distance, because that's the number one metric we care about, but also the accelerometer. And the accelerometer measures 1g for being straight up and down. And the thought here is we want to, if the accelerometer is less than 0.8, that means it's leaning severely or it's just fallen over, and that's a huge negative reward. So for this, negative 500 is really big. And then if it's greater than 0.8 but less than 0.98, it means it's leaning, and we want to, or at least I wanted to not just be as greedy as possible, but also wanted to try to smooth out the motions. So it wants to take a large step. It'll get rewarded for taking a large step, but also I wanted to also be some penalty if that step results in the robot leaning a lot. There's a lot of wasted motion. And then here, this is used to prevent some noise from being a reward. So the distance gained has to be greater than 50. And also it doesn't reward a small step. So we're only really rewarding a really nice, clean, large step. And a large step is something, in this, the raw data is something like 100 to 200 to 300, something like that. The raw data being the analog signal being read by the distance sensor. And then here, since there's 1 foot that's going to be planted, we want to ignore the distance from that foot, because there's a lot of erroneous readings you could get with these distance sensors, since they're reflective, and especially if the robot's far away, and you'll see this in the results, they're ultrasonic sensors, and if the reflective part of the robot is angled. The reflection can be angled such that the sensor doesn't see the reflected signal back to it, and then you can get some really wild readings. So this just helps ignore any readings that we don't need anyways. And then the reward is the distance sensor reading divided by 10, because that makes it, there's just, for the scaling of the rewards, it was chosen to use values, around the 10, 100 range. So it looked nice to have, a good step might result in the signal returning a 200 divided by 10. It makes it 20, so it made it a nice value. And then the accelerometer could, if even though you got 20, you're leaning a lot, it only makes it 10. So it made it a nice balance. And then there's a -1 here for any step, just in case there would be nothing here. So there'd be some negative reward for an action taken with no value here. Here the reward list is appended to, so we can store it for later. We print the reward. And then here, for the Bellman equation, we're getting the old Q value. And then here, according to the Bellman equation, we're calculating the temporal difference. And then just to show the Bellman equation again, it's the current Q value plus the temporal difference times the learning rate, and the temporal difference is the maximum Q value. Actually, this is a better one to look at. Here is the max Q value for the state you're in now. So you're updating the Q value from your last state. So this is implemented here for the temporal difference, and then we have our new Q value. So we're just implementing the Bellman equation here. And then that new Q value is put into the Q table for the last action we took, for the last state we were in. But notice it's based on the action that took us out of that state. And then we print, and then there's a debug line. So the debugs work by creating pauses right before you take a step, and then right after you take a step. And here we increment the number of steps. So each iteration through here, we take a step, we implement the step counter, and then every 50 steps, we save data to a network drive. So we're saving the Q values, and then the steps per episode, the reward history, and the action history. And what's nice about this is so if the computer crashes, or there's a bug, or power goes out or something, or the robot breaks, you can stop this cell, and you can start it up again, and you can just reload in the most recent Q table and resume from where you left off. And that's pretty much it for the version 2. The biggest difference between version 2 of this and version 1, version 1 had a different environment table, and it also since it was designed to take a bunch of little steps, it not only its terminal state not only had not only had an in stop and then the accelerometer, but it also stopped after it took 500 steps, and then it also, the data that was stored was assumed to be an array of 500, which created some issues, which we'll get into in the results. So the results. Okay, so first we'll look at version 1 results. And since the Q learning algorithm is driven by rewards and achieving the maximum reward, a really good metric for how the learning algorithm is progressing is to look at the rewards over time, or rewards over episodes. So we're going to be plotting the rewards history for version 1. Remember, version 1 usually took 500 steps, little steps per episode, and most steps would not have a positive value. There was an issue when I was recording this that the intent was just each time I record data, the rewards list would just be the entire list plus the most recent, but that accidentally erased it, cleared it, or reinstantiated it so that it was empty. So I have to piece together some of the rewards to get a continuous data set. So that's what some of this code here is for. So what this does is here we're loading a NumPy array from a file we saved during training, and then here we're summing up all the steps in in a particular episode. So there'll be 500 steps, and then this gets stored into this array here, and then we can plot. We just plot episode versus the sum of the rewards for that episode. And there's a story that can be told with this data. So most of the time was spent in version 1 of this, and the reason why most of the time most of this project was spent learning with version 1 of the algorithm. And the reason why that is because as it was training, and it would take a while for each one of these episodes to record. So it could, each recording, it would be about an hour between episode recordings, and then sometimes, I wouldn't let it run overnight because I was afraid something would break or something would break, or something would happen and I'd have to restart. So it took a long time to do this. A lot of times there would be a considerable break between a collection of data that I could plot to look at this. So this, over a longish period of time, looked promising if you look at the regression line. So this is just a line plot with a regression line. And the regression line was pointing up. And even like here, you can see that there are some very positive peaks. So not only is the regression line up, we're hitting new maximums, but something happened. So this peak here is this peak here, and it kept training, and then I had to adjust something broke on the robot. I had to make an adjustment. I noticed the feet were slipping. I added something that give the feet better traction, and the results plummeted. And in that algorithm, it took 500 steps per episode, usually. And you could have a negative 11 as, if the robot didn't really do anything. So the worst, if the robot doesn't do anything to get any reward for every 500 step, it's 500 times 11, so negative 500. And then so here you can see that basically there's almost no positive reward for any step for a lot of times. It's not good. By the way, I left something out up here. I think I didn't include, so there were some data sets, not all episodes had 500 steps, so it wouldn't save data. So what I did was, for those that didn't have 500, I calculated an average and then plugged that average in for any missing sets here. Anyway. So it took a long time to get to this, and then I realized that I'm going to have to reevaluate what I'm doing here. Here I have a video of a very early training. This wasn't even a training episode because it's not 500 steps, but it's a shortened version of one training episode. And so the steps taken here, these are training steps though that would have been in the version 1 training algorithm. So a bunch of little tiny steps like this. Also, I'll point out one difference. Originally, there was only one distance sensor that was planning on being used, and then that was expanded to 3. And then, in version 2, it was using a totally different distance sensor. But distance sensor became a big issue. Anyway, I'll resume this. So there you can see part of the lift routine. And then it sets it back down. Okay, so that was version 1. And version 2, there was a bunch of changes made. I added a wooden track with grip tape on it. I changed out the distance sensors. And, I totally changed the motions the robot would take. So I gave it the framework to be able to move much easier, to walk much easier. So defining a fixed X position actually made it much easier for the robot to train and actually walk. So, in version 1, it was 500 steps, wasn't often moving the robot very far. Once I made those changes, it would reach the end of the track in about 15 steps usually. So here, since it's not taking 500 steps, and I made a mistake in not recording the number of steps per episode, I can't do a sum of episodes per step, or steps per episode. But what I can do is just show the distance gained per step, because there's so much more distance gained in any one step that it actually makes it possible to just look at that data. So you can look at, you get an idea of what the reward is, because the reward is primarily the distance gained. And so this is plotting as a baseline. In the Q-learning algorithm, epsilon being set to 0, so it's not using any learned steps, so it's just taking random actions. And then this could be compared next to the Q-learning algorithm to see what the differences are. So that there's a difference there, and you could see over time if that is actually getting better when epsilon is not 0. So the first thing that jumps out from this is the data is noisy. And this has to do with the reflection of the distance sensor, and the robot's getting slightly angled, and the sensor is not picking up a good reading. But if you look through that and ignore it, you can see that it takes a lot of steps that move it in a positive direction. And I'm not sure why it kind of goes in this sinusoidal pattern here, where it seems to very periodically, very repeatedly take steps, that a bunch of steps that don't have a very good result, and then some that do, then some that don't, and some that do. You can see that through the data here. And then here, this is plotting in the same technique, just plotting the distance per step after 2,850 training steps. With the epsilon of 0.9. By the way, the epsilon was trained at 0.9, and then the learning rate and the learning rate and the discount factor, these were both 0.9, and that was primarily because I wanted it to try to learn fast, and I want the discount factor to be high because I want this to have a lot of influence on the rewards it gets, so that it maximizes the path to be heavily rewarded by the result of the of the action taken. So it should learn quicker. Okay, so here you see the same sort of pattern. Maybe not quite as not quite as much. It seems like maybe it has a higher number of steps that are positive before it dips down to 0. And then here I have a video we can watch of a training episode. Okay, so you can see the robot leaning left and right, and then it has an arm stick out to help it tilt over, to get it to be on one foot, to free up the other foot to move. And then this is, like I said, the distance you see the foot moving forward, it's fixed. But what's not fixed is the height that the robot can have. So one of the things that it should be able to do is it should learn any motion that causes it to any motions that cause it to lean. It should be better about not running into the situations where it causes it to lean left or right. It should certainly not fall over, which it definitely did do, and I don't have a video of that, but I'd rather not have to relive those instances. And then it should also not, it should learn not to get into the positions where it rubs up against this divider, causing the foot not to move, which is what is happening, I think, when you see the steps that gain 0. It's probably just because the foot is jammed up against this and it can't move forward. Okay, so I took that data, and since it was noisy, I filtered it. And here, this you can see that with the data filtered, that actually most steps were based on this filtered data. And the filtered data is a low-pass filter. It takes into 15 samples, combines 15 samples into one filtered sample, and then I plotted it. And cleaning it up, there is definitely some variation in the steps gained, but they're almost all positive. There's a few down here that are negative, and those are most likely either due to the robot falling over or the robot getting into a position where the foot's stuck up against the divider. And you can tell as it trains, you see these big negative dips. Oh, they also could be because of erroneous data. We're trying to filter out the erroneous data, so maybe that these are more likely to be actual valid results, especially these values like negative 20. That's a very likely good result. Even negative 40. Yeah, possibly this one too. And likely the same thing is true with the positive ones. 40 is a very likely, very good result. 60 might actually be, might be some noise on top of a good result. But unfortunately, and this is mostly due because the x parameter is fixed, the regression line's flat. So it doesn't look like it's really getting better over time, but not so much better over time, other than the lowest values seem to get better, but then it still does have some instances where it's not gaining any distance. And then here I've done a side-by-side plot of filtered data. So this is the training data with an epsilon of 0.9, and then this is the random only, so epsilon of 0. And It's not exactly an apples-to-apples comparison here because the x-axis is different, but I will say it looks like this early part of the data, maybe matches this, and then as this continued on, it did improve. So it looks like it is working, but needs more training to be conclusive. So ultimately, I would say the results are inconclusive. And then finally, what I decided to do was try to recreate the first set of data. I didn't actually have the number of steps per episode to do it. So the first version 1, it was number of steps per episode, so the sum of rewards. Here I did the same thing, and if you don't filter the data, it actually looks very positive. So I'm not 100% sure if this is real or if it's just an artifact of data. I tend to believe that this is just what happens when you have a small data set that's noisy. And with that, I draw my conclusion. So thank you for listening. I hope you enjoyed it.